Okay, so good morning, everyone. We finished chapter 9, which was about Gauss elimination, and we will start today with chapter 12. So we are not going to take chapter 10 and chapter 11. We'll move on to chapter 12. And chapter 12 is about iterative methods for solving systems of linear equations. In this chapter, we are going to look at the difference between the Jacobi and the Gauss-Seidel method. Then we see what we mean by diagonal dominance. We see what is relaxation, and then we can see how we can have some iterative methods for systems of nonlinear equations. The idea behind the iterative methods for solving system of linear equation is to convert the system from the form of ax equal to b into a form of x equal to cx plus d. So from ax equal to b, we are going to convert it to x equal to cx plus d. This is just like the idea of the fixed point iteration, where you had a fx equal to 0 and we convert it into the form of x equal to g of x. So same thing we do here. We said we'll make this into an iterative procedure by making on one side xi and on the other side xi plus 1. The same thing we do here. We keep one side as j minus 1 and the other one as j, or you can say j and j plus 1, however you like to call it. It's an iterative process where on one side you have a guess value and the other side you'll get the answer for the next iteration. If you have a system of equations like a11 x1 plus a12 x2 plus a13 x3 so on, you can write it in the form of, if you keep x1 on one side and you take all this to the other side, so it will become b1 minus a12 x2 minus a13 x3 or minus a14 x4 divided by a1. Of course, that gives you x1. We can do the same thing for x2. You keep this here and you take the rest of the things, you take them on the other side. So you'll have b2 minus a21 x1 minus a23 x3 minus a24 x4, and we divide it by a22, so you get x2, and so on. For all the variables, you can do the similar procedure to find equations for finding all of the unknowns. So this is the same thing written again, but just to see that for x1 we have 0 and then the coefficient for x2, coefficient for x3 in this one, and we have some constant here. So you can say that this is just like having a matrix C which is 0 in the diagonals, because all of these are zeros, and then we have the coefficient for x2, x3, x4 here, and then we have some constants here. So ax equal to b is converted in the form of xj equal to cxj minus 1 plus d, where of course he's saying the diagonal elements in the C are zeros. So this is how we convert ax equal to b into the form of x equal to cx plus d. Of course, we don't have any complicated things to do, just that you are going to rewrite your equations in this form, and then you go ahead with solving. Of course, the stopping criteria for such a process, because it is an iterative process, you are going to find the approximate error. Now, the approximate error, if you have x1, x2, x3, then you can find the approximate error for x1, for x2, and x3, because all of them are changing with each iteration. Then usually what we do is that if we have a stopping criteria, let's say of 1%, then you are going to make sure that the approximate error for each one of them is less than 1%. Okay, so you don't just look at one value, but you have to find error for all the unknowns. So this is the Jacobi iteration. It says the new values can be found using the old values by rearranging the equations. Let's take this example. So use Jacobi iteration to solve the problem. Now, the first thing that you are going to do is you rearrange the equations for x1, x2, and x3. So first equation, we'll use it for x1 is 7.85 plus 0.1 x2 plus 0.2 x3 divided by 3. Then the second equation, we can use it for x2 minus 19.3 minus 0.1 x1 plus 0.3 x3 divided by 7. And then x3 you can use it from the third equation, 71.4 minus 0.3 x1 plus 0.2 x2 over 10. Then we need some sort of initial guess value. I'll say x0. I'm putting the 0 up so that I differentiate between those x where we have x1, x2, x3, and this one up so that we know that this is the number of iteration and it's not x1, x2, or x3. I can take any initial guess value that I like, since these are not variables coming from a physical system, so I don't know what sort of initial guess values I need for them. So I take any guess values. I can take, for example, 0, 0, 0, 1, 1, 1, 1, 2, 3, 1, 0, 1. Anything. These are guess values. You take anything that you like. Let's say I'm going to take here now 0, 0, 0. This is my initial guess value. I'm going to take all of them to be equal to 0. Now the first iteration, x1 is equal to, from the equation, 7.85 plus 0.1 into x2 value, of course, is 0 plus 0.2 x3, and that is also 0, divided by 3. So 7.85 plus 0 is just 7.85 divided by 3. Please become small. 7.85 divided by 3. So 2.617. Then x2 is minus 19.3 minus 0.1 x1, which was 0 from the previous iteration, plus 0.3 x3, which is also 0, divided by 7. So that again becomes just minus 19.3 divided by 7. So 19.3 negative divided by 7 is minus 2.7 2.757. And then I have x3 is 71.4 minus 0.3 x1, which was 0, plus 0.2 x2, which was 0, divided by 10. Of course, 71.4 divided by 10, that's easy. So 7.14. So my x1, that's the value after the first iteration, is 2.617 minus 2.757 and 7.14. I can find the errors after the first iteration. It's going to be absolute value of 2.617, that's for x1, minus 0 over 2.617 into 100%. For x2 will be minus 2.757 minus 0 over minus 2.757 into 100%. And for x3, it's going to be 7.14 minus 0 over 7.14. Of course, since we are starting with the zeros, then we know that the whatever value you get, you'll have 100% error. So that's the error in the first iteration. Then you go on for iteration number 2. So x1 now is just like we had it before, 7.85 plus 0.1, and x2 value is minus 2.757 plus 0.2, I think. Yeah, 0.2, and x3 value is 7.14 divided by 3. So I have 7.85. Plus and minus becomes minus 0.1 multiplied by 2.757 plus 0.2 multiplied by 7.14 divided by 3, and I get 3.0007, so that's 3.001. And x2 is minus 19.3 minus 0.1 x1 minus 0.1 x1 is 2.617 plus 0.3 into x3 divided by 7. So I have minus 19.3 minus 0.1 into 2.617 plus 0.3 into 7.14 divided by 7. So that's minus 2.489. And x3 is 71.4 minus 0.3 into 2.617 plus 0.2 into minus 2.757 divided by 10. So I have 71.4 minus 0.3 into 2.617 plus 0.2 into 2.757, but minus divided by 10, 7.006. Those are the new values. I can find the approximate errors in all the three values of the unknowns. For x1, I have the new values 3.001. So I have 3.001 minus 2.617 divided by 3.001 into 100. So I have 12.8% error. In x1. The new value for x2 is 2.489. So I have 2.489 minus, then minus and minus becomes plus 2.757 divided by 2.489. Of course, since I take absolutes, I don't need the minus sign. So the error is 10.767. So I'll say 10.8% error. And then I have 7.14 and 7.006. So 7.006 minus 7.14 divided by 7.006 into 100. So 1.9%. Of course, ignore the minus sign. Of course, always you consider the maximum of these values and you stop according to the maximum error. 12.8% is still a big error. So let's have another iteration. So x1 is equal to, maybe I can view split better. So that's the equation for x1. 7.85 plus 0.2 into minus 2.489 plus 0.3 into 7.006 . So 7.85 plus 0.2 into 2.489 minus plus 0.3 into 7.006 divided by 3. So I get 3.151. And x2 is minus 19.3 minus 0.1 into 3.001 plus 0.3 into 7.006. So minus 19.3 minus 0.1 into 3.001 plus 0.3 into 7.006 divided by 7. So that's minus 2.4998 and x3 71.4 minus 0.3 into 3.001 plus 0.2 into minus 2.489 over 10. So 71.4 minus 0.3 into 3.001 plus 0.2 into 2.489 with a minus sign is this divided by 10, 7.0002 to 7.0002. Okay, so I can find the errors here and I can continue. Let me go to Excel and see how the numbers are changing there. So I have x1, x2, x3. I have iteration number. 0, that's the initial guess. 1, 2, 3, 4, 5, 6. Okay, I'll go up to 6 iterations. We started with 0, 0, 0. 0. For x, I need the equations. Okay, so this is 7.85 plus 0.1 multiplied by x2 value plus 0.2 multiplied by x3 value divided by 3. This is minus 19.3 minus 0.1 multiplied by x1 plus 0.3 multiplied by x3 divided by 7. This is 71.4 minus 0.3 multiplied by x1 plus 0.2 multiplied by x2 divided by 10. And then I just drag this on. I'll get the other iterations for them. And I can see that it is converging to the true value, which is 3 minus 2.57. I think we made some error in this calculation, maybe because the answer that we got was a bit different here. The rest of them are same, only this one seems we made some mistake there. The errors is absolute value of the old value, new value minus the old value divided by the new value multiplied by 100. So as we said, first iteration we get 100% error. Then we got 12.8, 10.8, 1.9. After that, we see we have 0.001, 0.4. So if we are just going to stop on 1%, we have reached 1% stopping criteria here. If you want to stop at 0.1, then this one is above 0.1, so you can't stop here, although the others are less than 0.1. In this iteration, you have gone below 0.1% also, so you can stop here. So we see very nice, easy method to find solution for system of the linear equations. I'll just highlight the maximum one to know that you always consider the maximum value when you are looking at the error. I guess this is the highest one here, 4.449. So whenever you want to consider, you consider the maximum value of the 3 errors. So those are the values. I think there's a mistake in this equation. Let us change it by the value that we have. Sure, the Excel has done better calculation. So it is 3.0008. Okay, so we don't have a wrong value there. Okay, so those are the values, and that's how we look at the system for solving using the Jacobi iteration. We'll take a problem from the book. So use the Jacobi method to solve the following system until the percent relative error falls below 5%. Same procedure, rearrange the equations. X1 is 27 minus 2x2 plus x3 divided by 10. X2 is minus 61.5 plus 3x1 minus 2x3. Please be careful, divided by minus 6. Students often ignore the sign of the coefficient here. X3 minus 21.5 minus x1 minus x2 divided by 5. We need an initial guess value. Last time we took it to be 0, 0, 0. This time I'll take it to be 1, 1, 1. So that we change, not every time have 0, 0, 0. Iteration number 1. X1 is equal to 27 minus 2 into 1 plus so 27 minus 2 is 25 plus 1 is 26 divided by 10 is 2.6. X2 minus 61.5 plus 3 minus 2 divided by minus 6. So minus 61.5 Plus 3 minus 2 means plus 1. So that's minus 62.5 divided by minus 6. Where is the calculator? So 61.5 plus 1, 62.5 divided by 6. Minus and minus cancels. So I have 10.417. And I have x3 is minus 21.5 minus 1 over 5. So that's minus 23.5 divided by 5. So minus 4.7 because I didn't put a minus sign there. So minus 4.7. So that's the first iteration value. 2.6, 10.417 minus 4.7. The errors, of course, comparing them to the previous values, which are 1. So 2.6 minus 1 divided by 2.6. So that's 61.5% error. 10.417 minus 1 is 9.417 divided by 10.417. That's 90.4% error. Minus 4.7 minus 1 is 5.7 divided by 4.7 is 121.3% error. So those are the errors that we get. Of course, the question says to stop at 5% error. So we have to continue with more iterations. I do iteration 2. X1 is equal to 27 minus 2 into 10.417 plus 1 times multiplied by minus 4.7 divided by 10. So X1 0. Yeah, sorry for getting disconnected. Yeah, sorry for being disconnected. If you can just let me know from where I was disconnected so I can start back from the same place. Okay, so what I did in Excel is just the calculations that we were doing. So I wrote the equations that we had, and I have found the values, and then I just took these values to the Word file. and the word seems to be stuck. So those are the values that we found from Excel. I said just to avoid the repeating of calculations, because we have already done the calculations here and we have the values. Also, I found the error in each iteration, same as what we had found here. I didn't find the error here, but we found the errors here. So you can see that if we take 1% as our stopping criteria, then we can stop here with this iteration, because we have reached, all of them have reached below 1%. Of course, I'm looking at the maximum of the errors. The one in the red is the maximum of all the three values. So we reached less than 1% here in all of them. So I stopped here. Then if you take 0.1% stopping criteria, then this is still below, not below 0.1, it is 0.4. So in this iteration, you can stop even if you take 0.1%. And we can see that the true root is 3 minus 2.5 and 7. So we are still very close. Even from the second iteration, we are very close to the actual values, which are 3 minus 2.5 and 7. So 2-3 iterations were good enough to reach the value. Then we took 12.3 from the book. Of course, it's asking a different method. We made it Jacobi iteration. We rearrange the equations to get for x1, x2, and x3. Then we take an initial guess value. I said in the previous example, we took it as 0, 0, 0. So now I took it as 1, 1, 1. You apply the equations for the first iteration. This is the value that we found. Then that's the second iteration value. Where are we? Since we were disconnected here, so let me repeat the Excel work here with this problem. So we have here the iteration number. We have x1, x2, x3. We have the errors. Iteration 0, 1, 2, 3, 4, 5, 6. We don't know to where we are going to go. We said the initial guesses are 1, 1, 1. X1 is 27 minus 2 times x2 plus x3 divided by 10. And we got 2.6 as we have it in the Word file. Minus 61.5 plus 3 times x1 minus 2 times x3 divided by, please don't forget the minus sign. Something students make a mistake that they forget the sign of the coefficient. Minus 21.5 minus x1 minus x2 divided by 5. So we did the first iteration and we got these values. We have something different here. Why is that? So let me check if the equation is right. So minus 61.5 plus 3 x1 minus 2 x3, which is right. Okay. So it was minus 61.5 plus 3, and I made it 62.5. Of course, it won't be 60, it will be 60.5 because we are on the minus. So I have a mistake here. So need to correct that. So it will be 60.5 divided by 6. So 10.0833. So this is not the case here. It's going to be 10.083. And then we said we can find the errors as absolute value of the new value minus the old value divided by the new value into 100. Of course, we can find this for the three values for x1, x2, and x3. So we get 61.5, 90.08, and 121.3. So 90.08 means 90.1. So sorry for that little thing. And then of course we can copy this all for the other iterations. Your stopping criteria is 5%. So you make sure that you go below 5%. So you look at the maximum one. Here, this is the maximum. That's the maximum. That's the maximum. That's the maximum. So whenever the maximum goes below 10%, oh sorry, 5%, which is stopping criteria, you can stop. Just to carry on and see what's the final answer. So it seems it is 0.5, 8, and minus 6. So if we stop here, so we are close 0.5, 8, and minus 6. It seems we are pretty close to the answer. So you can stop here. Of course, here you can see the approximate error again goes above 5%, but you don't have to worry about that. The first time you get all of them becoming less than 5%, you can stop there as your final solution. Okay, so I'll just stop here. I'll not bother about the next values. Or no need for all this, since we found it using Excel, so we can just put the values here. So those are the values, and we stop. So that's my answer that I get according to the 5% stopping criteria. Okay, so that's the Jacobi iteration. Okay, we are still online. We can take a 5 minutes break, and then we can join back. If you have questions, you can ask. Keep it like this, just to make sure that I remain connected. Okay, so welcome back after the break. So we have seen the Jacobi iteration method, and we have seen it's like the fixed point iteration, and you find the errors based on all the three variables. If you have 4, 5, 6, then on all of the values. Another method that we have is the Gauss-Seidel method. The only difference between the Gauss-Seidel method and the Jacobi iteration is that the Gauss-Seidel method says that, where is the Excel? The Gauss-Seidel method says that, let me give from here, that we are finding these values based on the old values of x2 and x3. Then once we come to x2, we are using the old values of x1 and x3. But the logic says that whenever you have a new guess value, it's going to be better than the previous guess value. So when we find x1, we use old value for x2 and x3 to find the value for x1. But once we come to find x2, then we already have a new value for x1. So the Gauss-Seidel method says that why to use the old value of x1 here? Why not use the new value of x1, since we already have a new value of x1? We don't have a new value for x3, so we can still use the old value for x3. Once you come to find x3, we already have a new value for x1 and we have a new value for x2, so use the new values where available. So here we are using the old values. Here we are using the old value, but it says that since we have a new value for x1, use the new value. And for this, he says use the new value for x1 and for x2. So this approach makes our convergence to be faster. You can see that we have reached the true solution much quicker than what we had earlier using the Jacobi iteration. So that's the only difference between the Gauss-Seidel and the Jacobi iteration. The Gauss-Seidel iteration says wherever possible, use the new values and don't use the old values. So I'll go back to this problem, which said use the Gauss-Seidel method. So we solved 12.3 using the Jacobi iteration. We'll solve it now using the Gauss-Seidel method. Now the equations and the procedure is the same. I'm still going to say x1 is equal to 27 minus 2x2 plus x3 divided by 10. The only thing here is that this is the old value, the old value. Minus 61.5 plus 3x1 minus 2x3. The difference is that this is the old value, but this is the new value. And x3 is minus 21.5 minus x1 minus x2 divided by 5. And both of them will use the new values because we have the new values available. So that's the difference between the Jacobi iteration and the Gauss-Seidel iteration. Gauss-Seidel iteration is considered to be an improvement over the Jacobi iteration. Let's take the same initial guess value. As 111. $27 minus 2 into 1 plus 1 over 10, we found it to be 2.6. So that won't change because in x1 we are still using the old values. Now once we go for x2, we have minus 61.5 and plus 3 times. Now instead of using the old value for x1, we'll use the new value for x1, which is 2.6. Minus 2 times x3 is still the old value divided by minus 6. I'll do it in MATLAB so I'll not make mistakes. So that's minus 61.5 plus 3 times 2.6 minus 2 times 1 divided by minus 6. So it's 9.2833. And x3 is minus 21.5 minus x1, of course, the new value, which is 2.6, and minus the new value, which is 9.2833. So minus 21.5 minus 2.6 minus 9.2833 divided by 5. So minus 6.6767. And of course, we can continue like this. To save time, I'll just go to Excel. I have all these values here. I'll just copy this 4. I hope I'm not going to need more than 4. The thing that changes now is that here, instead of using the old value, we use the new value. Here, instead of using the old value, we use the new value, and we use the new value. And then I can copy this. And we can see again, of course, here the thing changes, that we have reached 5% here, and we are close to the true solution, which we said is 0.58 and minus 6. Comparing this to the true solution here, which was 0.5, we can see we are a bit away from 0.5. This is 8.04, which is 7.999, much closer to 8. And this is minus 5.999. This is 5.98. So this solution is much closer to the true value than the solution that we had here. Even this is maybe closer than this solution. But we are stopping based on the 5% stopping criteria. So that's the answer that we get. So this, the Gauss-Seidel iteration, makes life much easier for us and helps us to reach the solution much quicker than what we had using the Jacobi iteration. Don't know why, but word is not working very well. Final answer is x1 equal to 0.496, x2 equal to 7.999, and x3 equal to minus 5.999. Using 5% stopping criteria. So that's the answer that we get using the Gauss-Seidel iteration. So that's just the difference between the Gauss-Seidel and the Jacobi iteration. In the Jacobi, we use new values. In the Jacobi, we keep using the old values. Jacobi, we use Gauss-Seidel new values. Gauss-Seidel new values. Jacobi old values. I have already showed you how to do this one in the Excel. The diagonal dominance, that's the convergence criteria for the Gauss-Seidel or the Jacobi. Both of them have the same criteria. It may diverge because it is an open method like the fixed point iteration. It is similar to fixed point iteration, but it will definitely converge. System is diagonally dominant. What do we mean by diagonally dominant? Diagonally dominant means that the AII, the absolute value, should be greater than the sum of the absolute values of all the other elements in that row. Three should be greater than 0.1 plus 0.2. Of course, we are not worried about the sign, just the values. 7 should be greater than 0.1 plus 0.3. 10 should be greater than 0.3 plus 0.2. If it's greater, then it is said that is diagonally dominant. And if a matrix is diagonally dominant, then it will definitely converge. It will definitely converge. If it is not diagonally dominant, it may diverge or it may converge. The chances that it will diverge is big, but it's not definite that it will definitely diverge. But if it is diagonally dominant, it will definitely converge. Fortunately, many engineering problems of practical importance satisfy this requirement that they are diagonally dominant, so we don't have to be very much afraid of this issue. You see the same equations but in different order. Here you start with an initial guess, and you can see that they are converging. Same equations, same initial guess, but different order, you find that it is diverging. So if you find that the system is not diagonally dominant, you can rearrange the equations to make it diagonally dominant, and then you can have convergence. Let's look at a problem. Okay, I'll take this one. It's a small one. It's problem 5.1. Now we see that three greater than 8 is not satisfied. 1 greater than 7 not satisfied. So in both cases, we find that the system is not diagonally dominant. If I take initial guess, let me go to Excel and we do like things there. So that's our equation. So x1, x2. Let's take 1 and 1 as initial guess. And this is, if I use the Jacobi iteration, I'll show both of them. 11 minus 8 x2 divided by 3. This is 5 minus 7 divided by minus 1. we see the numbers are getting bigger and bigger, so most probably they are diverging. So that's the Jacobi iteration. What if we had the Gauss-Seidel iteration? This doesn't change. This will just use the new value now. We still see that it is diverging. The reason that we don't have diagonal dominance. Now we swap the order of the equations. We say 7x1 minus x2 equals to 5 and 3x1 plus 8x2 equal to 11. In this case, 7 is greater than 1 and 8 is greater than 3. So the criteria for diagonal dominance is satisfied. So let me write it here. Uh, 7x1 minus x2 equal to 5 and 3x1 plus 8x2 equal to 11. Then, as we said, 7 is greater than 1 and 8 greater than 3. Convergence diagonally dominant, hence it will converge. Let's see how that affects our solutions. I have x1, x2, same initial guess values, but the equation now changes. This is 5 plus x2 divided by 7, and this is 11 minus 3. I'm using the Jacobi iterations, the old value, divided by 8. And we see that the final answer 0.86 and 1.05. So from the second iteration, maybe we are very close to the true solution. What if we use the Gauss-Seidel iteration? The thing that will change here is the new value. And we see that 0.86 and 1.05, almost from the first iteration we are there. So just changing the order of the equations helps us to solve this problem of divergence, because the system becomes diagonally dominant. So diagonal dominance is the key for convergence when using the Gauss-Seidel or the Jacobi iteration. So you always make sure that you have this criteria satisfied. So I'll just take the 5 iterations, I'll put them there. So this is Jacobi iteration. And that's the Gauss-Seidel iteration method. So that's the difference between the two methods. And diagonal dominance, of course, very important to see whether you are going to have convergence or you don't have convergence. I'll go to problem 12.7. He says, of the following three sets of linear equations, identify the set or sets that you could not solve using an iterative method like Gauss-Seidel. Show using a number of iterations that it is necessary that your solution does not converge. Where are the three sets of equations? Okay, so set one. Our matrix is 8, 3, 1. The variables are x, y, and z. -6, 0, 8, 2, 5, -1. Now, if you look at the convergence criteria, 8 greater than 3 plus 1, that's okay. 0 greater than 6 plus 8, this is not okay. So it's not satisfying the diagonal dominance criteria. 1 greater than 2 plus 5, also not okay. So this is not diagonally dominant, so this is going to diverge. Can we do something about it? Can we make it to converge? If we swap second and third row, we'll have 8, 3, 1, 2, 5, -1, -6, 0, 8. So 8 greater than 3 plus 1, which is greater than 4. 5 is greater than 2 plus 1, so 5 is greater than 3. And 8 is greater than 6 plus 0. So our system becomes diagonally dominant, and we can see that it is going to converge, since it is now diagonally dominant, hence it will definitely converge. Okay, so here, of course, you can see that once you use this order, you are going to be dividing by 0. So that one is definitely diverging. There is no way out of it. Set number 2. Put it in the matrix form. 1, 1, 6, 1, 5, -1, 4, 2, 2. Of course, if we check the criteria, 1 greater than 1 plus 6, 5 greater than 1 plus 1, 4, 2 greater than 4 plus 2. Not satisfied, not satisfied. So it is not satisfied. So this is going to be not diagonally dominant. So there are big chances that it might diverge. What if we swap if we swap row 1 and 3, so we get 4, 2, 2, 1, 5, -1, and 1, 1, 6. So 4 greater than 2 plus 2, 5 greater than 1 plus 1, and 6 greater than 1 plus 1. Satisfied, satisfied. This is, it's not greater, it's just equal. So there are chances that it might still converge, because okay, we don't have it greater that, but it is still equal. Please keep in mind that the diagonal dominance criteria is greater. It's not greater than or equal to. Equal to doesn't mean diagonal dominance. It must be greater. But here we have it just equal. So it's not really diagonally dominant. But you can check, he says in the question, show using any number of iterations that it is necessary that your solution does not converge. So you can check whether it will converge or diverge here. It seems that since the other two are 5 is much greater than 2 and 6 much greater than 2, so most probably this is also going to converge. It's not going to diverge. Set number 3. -3, 4, 5, -2, 2, -3, 0, 2, -1. 3 greater than 4 plus 5? No way. 2 greater than 2 plus 3? No. 1 greater than 2 plus 0? No. So it's not diagonally dominant in any of the rows. Now, for example, if I take this row and I keep it for x2, if I make this the second row, for x1, of course, it's not converging. If I take it for x2, then 4 should be greater than 3 plus 5. It is not the case, so it's not going to work for x2. If I make it for x3, then 5 should be greater than 3 plus 4, which is not going to be the case. So I cannot use that anywhere. This doesn't work for x2. What if I make it for x1? Then again, it's the same case. 2 is not greater than 2 plus 3, and 3 is not greater than 2 plus 2, so it won't work. If I take this x1, then 0 is not greater than 2 plus 1, so that won't work. For x3 already it's not working. Maybe for x2 it can work. So I can have this to be my second equation. And then you decide the other two, how you can have them. If you take this for x1, then 3 is not greater than 9. If you take the last one for x1, the second one for x1, then 2 is not greater than 5. So in both cases, it won't work. If you take this for x3, then 5 is not greater than 7, and 3 is not greater than 4. So maybe if we take this one, because at least 2 closer to 5 than 3 closer to 9, and this one still okay, if 5 is a bit close. So if we take this for x1 and take this for x3, and then you see whether it's going to converge or diverge. So we said this for x1, x2, and x3. We can check in Excel. We have x1, x2, x3. We'll take some initial guesses. 1, 1, 1. So we said we'll use the second equation for x1. So minus 3 minus 2 times this plus 3 times this divided by minus 2. X, Y, Z, as this is calling them. So we are using this for x1, x, this for y, and we'll use this for z. So y equation says 1 plus z. Of course, I'll use the Gauss-Seidel iteration divided by 2, and this is z equation is 6 plus 3 times x1 minus 4 times y divided by 5. I think 111 is the solution here, so don't, well, I'll not start with 111. Let's say I start with 333. And of course, we can see that the values are diverging. They get bigger and bigger and bigger. 111 is the actual solution, so therefore it directly converges. What if I have 1, 2, 3? We still see that it is diverging. What if I have 0, 0, 0? We can see that it is still diverging. So taking other guess values other than the true value, of course, then there's nothing to do iteration there. We see that it is always diverging. What if I have something close to the true values? It still diverges. So we can see that once the system is not diagonally dominant, then it is most probably is going to diverge. So that's the Jacobi and the Gauss-Seidel iteration. Time is less, so I'll stop here. If you have questions, you can ask. Yes, please go ahead. Test 2, we'll see up to where we can reach next week. Then I'll tell you what's the material for test 2. Any questions regarding the lecture?